This lecture introduces the acid-base reactions of carboxylic acids. Carboxylic acids have an acidic proton that can be deprotonated by bronzite bases. They also have an electrophilic carbonyl carbon and a nucleophilic carbonyl oxygen. Under strong acid conditions, carboxylic acids can protonate. In this case, the carboxylic acid is functioning as a bronzite base, and we have corresponding strong acid like sulfuric acid or phosphoric acid. Let's look at which oxygen is more likely to protonate under strong acid conditions. If we draw the equilibrium reaction for the first reaction, we protonate at the carbonyl oxygen. In this case, we can see that there is the possibility of drawing a resonance form. So this conjugate acid is stabilized by resonance. Now let's consider the other oxygen. If we use this oxygen to protonate, we're going to draw our arrows and protonate the carboxyl oxygen. In this case, we can see that we have no possibilities for resonance to stabilize this conjugate acid. And so with this reasoning, we can conclude that this is the more likely reaction, with this carbonyl oxygen being more likely to protonate an acid. Now, carboxylic acids also have an acidic proton and can function as an acid. So if we treat it with a base, we can deprotonate this acidic proton and draw the conjugate base in this reaction, which is the carboxylate anion. This is also stabilized by resonance. And the negative charge is delocalized across both oxygens. The pKa of most carboxylic acids is around 4. Acetic acid, which is this example here, has a pKa of 4.7. Benzoic acids, which have a phenyl group at this position, have a lower pKa of about 4.2. This is a list of bases that can be used to deprotonate carboxylic acids. They are listed in order of increasing basicity, and we determine this using pKa's of the conjugate acid. If you look at a reaction and you want to know whether it can deprotonate a carboxylic acid or not, what you're going to do is look at the relative pKa's of the acids on both sides of the reaction. For instance, if we have bicarbonate, we're looking at this equilibrium reaction, and bicarbonate is going to deprotonate to give us the carboxylate and form carbonic acid. And so you're looking at the relative strengths of the acid on this side, which is the carboxylic acid and has a pKa of about 4. And then we're looking at carbonic acid, which has a pKa of about 6. We know that we're always going to react the stronger acid and stronger base to go to the weaker acid and weaker base. This is the weaker acid, and so the reaction favored is going this way, where the carboxylic acid will be deprotonated. The acidity of carboxylic acids can be exploited when we want to separate a mixture of compounds. This is called extraction, and the basic principles are acid-base reactions and solubility. What we're looking at is if there are functional groups in an organic compound that make it acidic, basic, or neutral, we can then treat it with the appropriate base or acid and convert it to its ionic form. If an organic compound is neutral, it's going to be soluble in the organic layer. If the organic compound is in its ionic form, it's more likely to be soluble in the aqueous layer. Using these principles, we can then do a series of extractions and separate these compounds. Now let's look at common functional groups in organic chemistry. We know the carboxylic acid is acidic. It has a pKa of about 4.7. We have alcohols. An aliphatic alcohol has a pKa between 16 to 18. A phenol has a pKa of about 10. And we have amines, which are basic and have pKa's about 35. Based on this knowledge, we can use a series of acids and bases to separate basic components from acidic components and neutral components. When we consider acidic components, if we have a carboxylic acid and an alcohol in the same mixture, we know that carboxylic acids have a lower pKa, and so if we use a milder base, such as sodium bicarbonate, it will deprotonate the carboxylic acid, but not the alcohol. Now let's look at a mixture of 4 compounds. Our goal is to separate them and isolate them in their pure neutral form. As drawn, all of these compounds are soluble in organic solvents. What we're going to do is do a quick mix of the organic solvent with aqueous acids or aqueous bases and try and separate them. Under extraction conditions, if we look at each of these compounds, we can tell that we have an acidic proton in cyclohexanol, and if we look at ethyl 4-aminobenzoate, we can look at the acids, bases, and neutral components. We have a basic component here, so we've got the amine, which can protonate with acid. For benzoic acid, we've got the acidic proton of the carboxylic acid, and since we have 2 acidic protons, it's important to know that there's a pKa difference, and so we can use that to our advantage. And finally, if we look at benzophenone, we can tell that under extraction conditions, this would be neutral. Let's first look at the common acids and bases that we use in extraction. So some of the common acids are HCl. It might be a 1 molar solution or a 6 molar solution or anything in between. We use H2SO4 occasionally. Some of the bases that we use are sodium bicarbonate if we want something really mild. And all of these are aqueous solutions. We use potassium or sodium carbonate, and we use sodium hydroxide or potassium hydroxide if we want something stronger. And again, this will be a solution. It can be anywhere from 0.1 molar to 6 molar. Experimentally, the first thing that we'll do is mix all of these and put them in an organic solvent, usually a solvent like dichloromethane or ethyl ether. So all of these are currently in an organic solvent, and let's first start by trying to isolate the amine component. So what we can do is we can treat this with 6 molar HCl, and that will result in protonation of this amine to form the ammonium salt, which means that now in our aqueous layer, in our water layer, we have the ammonium salt, and it's going to be in the water layer because it's ionic, and everything else is going to remain neutral, and so these are all going to go in the organic layer. So in our organic layer, which may be dichloromethane or ether, we've got everything else. We've got the alcohol, we've got the carboxylic acid, and we've got the ketone. In order to isolate the amine in its pure form, we are going to now treat it with base, so we can treat it with sodium hydroxide. Again, it's an aqueous solution, and we're going to deprotonate this ammonium salt and form our amine. And so we have purified 1 component. In our organic layer from the original mixture, we had a mixture of the alcohol, acid, and ketone. What we can now do is try and separate these 2. And we want to start with the milder base first, sodium bicarbonate, so that we can pull out just the carboxylic acid. So now we're going to take all of these which are in the organic layer. We're going to treat it with sodium bicarbonate. So we're treating it with saturated solution of sodium bicarbonate, and we should get the carboxylate salt. And that's going to be in the aqueous layer. And in order to isolate that, we are just going to treat it with HCl, and we will isolate our carboxylic acid. And so we have separated our second component. In the organic layer, from the sodium bicarbonate wash, we had the alcohol and we had the ketone. So what we're going to do now is treat it with a slightly stronger base like the hydroxide to pull out the alcohol. So we're treating this with sodium hydroxide. So we can say 3 molar sodium hydroxide. And in our organic layer, we now have purified the ketone, because remember, it's not going to react with anything. So this is our third component that's purified. In our aqueous layer, what we have is the deprotonated alcohol. So we've got the alkoxide. And what we're going to do is treat this with acid. So we can treat it with mild acid, and we're going to protonate to get our alcohol. And so we've purified our fourth component. Now pause the video and predict in which layer each of these compounds will be isolated in their pure neutral forms. The first thing to do is to analyze our compounds. We know that benzoic acid has an acidic proton. We know that p-nitroaniline has a base component, and we know that mesitylene is neutral. So if we have a mixture of these three compounds in organic solvent, and we treat it with 6 normal HCl, so this is an acid, it will react with the base in the mixture, and so this acid-base product is going to be in its ionic form, and it's going to be in layer A, and it's going to be in its protonated form. When we treat this aqueous layer with this ammonium salt with 30% NaOH, we are going to deprotonate the ammonium salt, and now this amine, p-nitroaniline, is reformed, and we're going to have it in the organic layer because it's going to be soluble in organic solvent, insoluble in aqueous solvent. And so D is going to contain the purified amine. Now this means that if we go back to our original separation, we treated with acid, the base reacted and was removed. In the organic layer, we had the benzoic acid still present. So we had benzoic acid, it was still present in its neutral form, and we had mesitylene. And then we treated with 5% sodium hydroxide. So now in this case, the acid is going to react with the base and is going to form an ionic compound and go into the aqueous layer. So what we have in E is the carboxylate salt, and what we have in F is mesitylene. So we have purified our second organic compound, and that's in F. And then we're going to take layer E, so this is our aqueous layer, and we're going to treat the carboxylate anion with 6 normal HCl, which means we're going to protonate the carboxylate, and so now it's soluble again in organic layer, and in the organic layer we are going to isolate our benzoic acid.